Hello everybody. In our series of lectures on basic electronics learning by doing, let us move on to the next. Before we do that, let us quickly recapitulate what we discussed in our previous lecture. You might recall that we discussed about an active diode circuit, how a normal semiconductor diode can be improved to become almost an ideal diode, and making use of such an ideal diode, which is actually the normal diode along with an operational amplifier. So this ideal diode was used in different applications, like making an half wave rectifier, then how a full wave rectifier can be implemented using such an op amp along with a diode to make an ideal diode. Then we also saw some variations of these, like the peak detector and the active positive clipper and clamping circuits, which are very useful in different wave shaping circuits. Now let us move on to the next important topic basically in electronics, that is design of oscillators. Oscillators are basically circuits which will convert a DC voltage into a sinusoidal voltage. You know about rectifiers. Rectifiers convert an AC voltage into a DC voltage. The oscillators will do just the reverse. It takes the power supply from the DC power supply, and the output of an oscillator will be a sinusoidal. Most of the time it will be a sinusoidal waveform, sine wave. Oscillators are very useful for different applications, especially in radio communication and things like that. So let us see how we can build oscillators using operational amplifier. That is what we are going to discuss this time. In order to build sine wave oscillators, as you can see on the screen, we need to use a well known amplifier. Any amplifier can be converted to become an oscillator, but you have to give a feedback. To become an oscillator, an amplifier should be given a feedback. You know already we discussed about that amplifiers, when I give negative feedback, many of the characteristics of the amplifier will improve. Now we never discussed about the positive feedback, we only talked about negative feedback. So negative feedback means what? Take the output, invert it in phase by 180 degrees with reference to the input and give, then you get a negative feedback. The feedback voltage should be out of phase with the input voltage, and therefore this negative feedback we have already seen improves several characteristics of the amplifier, like input resistance, bandwidth, output resistance, distortion, etc. But if I now take the part of the output voltage and give it in phase with the input voltage, then it becomes positive feedback. In an amplifier, if I implement positive feedback, it normally results in oscillations. When we want to use amplifiers for amplification purposes, we will not use positive feedback, we will only use negative feedback. But when you want to convert an amplifier into an oscillator, then you go in for positive feedback. We have also derived in one of the earlier lectures the condition for a gain of an amplifier with feedback, and that you can see in the screen, A by 1 plus A beta. You may remember that expression, AFB, which is the gain with feedback, is equal to A, the gain without feedback, divided by 1 minus A beta, where again beta is the feedback ratio, the fraction of the output which was given at the input. This minus sign is what you get for positive feedback. For negative feedback, the sign in the denominator will be plus. So For an amplifiers we would have used the formula AFB is equal to A by 1 plus A beta, but when you want positive feedback you would find the same derivation, we can do that. You would find it will become 1 minus A beta. When you impose the condition, the output should be in phase with the input, which is corresponding to positive feedback. So because you have a minus sign, it introduces very interesting situation here. A generally is a large number gain, beta is a small fraction. Sometimes it may so happen that when A beta becomes equal to 1, that is when A is equal to 1 by beta, then A beta becomes 1. When A beta becomes 1, you know what happens to the denominator. A by 1 minus 1, 1 minus 1 is 0, therefore the denominator becomes 0. In any fraction if the denominator becomes 0, you know it becomes infinity. The gain with feedback is now infinite. What do you mean by that? Infinite means very large number. Or what is feedback in general, what is gain in general? Output voltage by input voltage, that is a voltage gain. Now when will this output voltage divided by input voltage become infinity? It will become infinity only when the denominator becomes 0. The denominator in this case is Vi, the input voltage. Therefore what it means is, when I make positive feedback in an amplifier, when I provide positive feedback and make the product A beta equal to 1, it is equivalent to saying I get an output voltage with 0 input voltage, that is the denominator becomes 0 in this expression. When the denominator becomes 0, expression becomes infinity, and therefore you get only output voltage. That means what? Without giving any input voltage you are getting an output voltage. So this is what we call oscillator. So you have not given it is an amplifier in which you do not have to give any input, but you get an amplified output signal, AC signal. Where from it is coming? It is generated out of the power supply voltage that you are given. Therefore I call that as a converter of a DC into an AC. You give only a DC supply for energizing the amplifier circuit, but you have implemented a positive feedback and you have made sure the feedback ratio in such a way that the gain into the feedback fraction is equal to 1. If you do that, you get an output sine wave without any input. That means it becomes an oscillator. So this A beta condition you will not get all the time, it has to be satisfied only at one particular frequency. You will see that this feedback will have to be given through some frequency sensitive components, reactive components, and therefore you would find this condition will be true only for one specific value of frequency corresponding to the reactance. Therefore only that frequency will be preferentially provided and the output will be having that frequency. If you want to vary the frequency, correspondingly you have to vary the reactive components that you have in the circuit. But in principle what I have so far explained is the most important criteria or the principle of oscillators. This condition A beta should be equal to 1 in an amplifier with positive feedback for generating oscillator is called Barkhausen criteria. Right. Now what happens to the output voltage for different values of A beta? If A beta is less than 1, then the gain will become increasing. AB V in is less than V in and the output signal will slowly die out, and that is what is shown here. The initial sine wave keeps on decreasing because it is less than 1 subtracting, being subtracting. If the A beta value is greater than 1, then A beta V in is greater than V in, and therefore the output voltage keeps on building up. When you give feedback, a larger portion comes through the feedback, so it increases the input voltage, and therefore the output will still further increase because it is just an amplifier. So you would find the sinusoidal voltage which starts with a small amplitude will start building up. This also is not a very desirable feature. The previous one where the amplitude decreases is not also what we want. What we want is something which will sustain the oscillations with constant amplitude. That happens when AB is equal to 1. Then AB V in is also equal to V in, because A beta becomes 1. So, both are V in, and therefore, there is no loss, there is no decrease, there is no increase, it maintains the same input, and therefore, you get the same output. That means you get a steady output sine wave. That is what is shown in the picture at the bottom. So, this is basically the idea behind the principle of the oscillator. But if you actually take any amplifier, for example, a RC coupled transistor amplifier, you know the output is always 180 degrees out of phase with reference to the input. This is a characteristic of RC coupled amplifier when you have common emitter configuration. So, this 180 degrees shift is already built into the amplifier configuration due to the common emitter configuration. So, if you want to have a feedback, the feedback should be positive. That means the input voltage should be in phase with the voltage fed back from the output. If you take the output directly from this amplifier and give it at the input, it is 180 degrees out of phase. Therefore, it will not be positive feedback, but it will only be a negative feedback. That is what we do in many amplifiers. So, for making positive feedback, you should introduce a phase shifting network between the output and the input, and then only give the feedback voltage. That phase shifting network you should make sure produces another 180 degree phase difference, so that the total phase difference becomes 360 degrees, which is equal to 0 degree phase. So, this is the idea. Use a normal amplifier which has got 180 degrees phase difference between the input and output. Use a separate network using some combinations of reactive components, so that it produces another 180 degrees in addition, and together both of them will provide 360 degree phase difference. And if you now give this fraction to the input and make sure that it is equivalent to the input voltage, then you would find you can slowly remove the input, and that this positive feedback alone will sustain the oscillations, and you will get steady sine wave output at the output. So, that is the basic principle of a oscillator. How do we introduce that phase difference of additional phase difference of 180 degrees? The simplest method we all know is to use resistance and capacitance in combination. A RC network we have already discussed when we discussed about the frequency response of amplifiers, a lead network and the lag network about which we talked about. So, you can use any one of this, either the lead or a lag. Both of them introduce a phase difference. We all know that any RC combination produces the phase. I have shown you on the screen a very simple scheme with a capacitor and the R in series, and you take the output across the resistor. Now, what is the output voltage? Output voltage is the output resistance R divided by R plus jXC into V in. This is a potential divider now. The C and the R reactive component and the resistive component form a series circuit as a potential divider, and you are taking the output across the R resistance, and therefore, the formula is R divided by R plus jXC into V in. The jXC is actually the reactive impedance of the capacitance. Xc is 1 by omega c, we all know that. So, the phase shift, what is the phase shift in this case? It is a Xc by R, that is, we have written here x1 by R, that is a phase difference phi. This simple RC network will automatically give a phase shift of x1 by R, where x1 is 1 by omega c, where omega is the angular frequency, which is equal to 2 pi f, where f is the frequency of the input sine wave. And therefore, you see for a given frequency the x1 will be different. The capacitance, capacitive reactance is a function of frequency. Therefore, depending upon the frequency, the reactance will change, and hence the phase difference should change. And therefore, you would find if I want, in this case tan phi can be 0 or infinity or any other value in between. If phi is equal to 0 or 90 degrees, then x1 is equal to 0. When x1 is equal to 0, tan phi is equal to 0 in this equation, in this formula, and therefore phi is equal to 0 degree. When r is equal to 0, the denominator, then this tan phi becomes infinity and phi becomes 90 degrees. So using one RC combination, you can have any phase difference between 0 and 90 degrees only, not more. You can always have less than 90 degrees, but you cannot have more than 90 degree by using just one RC. Even 90 degrees is an extreme case, 0 degree and 90 degree are two extreme cases. Therefore, a phase shift due to an RC circuit is always less than 90 degrees, and it is also a function of frequency. These two important points we should remember before we go into the design of oscillator. So if we want in an amplifier, which like a common emitter amplifier, which produces 180 degree phase shift between the input and output, and if you want that another additional phase shift of 180 degrees, then how many RC networks you require to have additional 180 degrees? What will be the answer? One RC network we have just seen can only provide at a maximum of 90 degrees. Therefore, it is always going to produce a phase shift which is less than 90. When it is less than 90, even 2 RC network cannot give 180 degrees, and therefore a minimum of 3 RC networks are required to produce total 180 degrees phase shift for a given frequency. So this is the principle of a phase shift oscillator. I will talk about it now. So let me just show you a circuit of the phase shift oscillator with transistors, then we will go on to the op amp, because the principle is the same. You have here a transistor, and if you look at only the first part where I show with my arrow with the pointer, you find this is nothing but an amplifier with a voltage divider bias R1 and this variable R. RC is the collector resistor, RECE gives you the emitter bias. So this is a basically an amplifier, single stage RC coupled amplifier, because you are coupling it with C here, RC coupled amplifier. Now what are we doing? We are taking the output, and you see it is brought back through this wire to the input, and at the input what are you doing? You are keep on combining series of RC set CR, that output is taken and given to another CR, that output from the R is taken to another CR, and that output is given to the input. So between this base, which is the actual input of the amplifier, and the collector, there is 180 degree phase shift we have already seen, and that 180 degree phase shift voltage is applied here. With this 3 combination of RC, 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 you try to produce another 180 degrees, so that totally it becomes 360 degrees, and then this voltage which comes from the output becomes in phase with the input that you perhaps given at the beginning. You have not given anything, this happens very fast. I will explain to you how this happens. Therefore this becomes the input voltage, and if the conditions are fine, ideal, then you find this input will get just amplified enough, so that after passing through 3 things again it becomes the same value as the initial value. So you get a constant input voltage, and this RC, 3 of them provide 180 degrees in addition to the 180 degrees that is produced by the amplifier, RC coupled amplifier. The total were 360 degree provide the necessary positive feedback, and therefore the output, if you take now from here another wire and connect it to an oscilloscope, you would find it will start oscillating. If it is not oscillating, all that you have to do is one of the bias resistors, I have put variable, you vary it slightly, then you would find at some position of this resistance, when the conditions are proper, when the gain becomes sufficient, you would find you will get a sine wave beautifully coming out at the output. So this is a simple RC coupled amplifier, RC phase shift oscillator constructed using a simple RC coupled emitter amplifier, common emitter amplifier. How will we do that in operational amplifier, using operational amplifier? You know, in operational amplifier we have another advantage. The advantage is you have both inverting and non-inverting inputs, so that whatever type of voltage feedback you want to give, you can give in principle. But now what we are going to do is, we are still going to use that 180 degrees out of phase as we did in the RC coupled amplifier that just now I showed, in the phase shift oscillator just now I showed. So there is a 180 degree phase shift, so that output is now taken and given to combination of 3 RC networks here, so that the phase here becomes just 180 degrees, additional 180 degrees, and it will be in phase with the input, and then this will start sustained oscillations and you will get the output. So this is the circuit corresponding to an RC the phase shift oscillator using op amp. You did not find much difference with the transistor amplifier, except that I have removed the transistor common emitter amplifier, and in place of that I have introduced a inverting amplifier using op amp, which we have all seen earlier. So now at some definite frequency f, 2 pi f will be omega, and you would find that will introduce at that frequency exact 180 degree phase difference with the combination of 3 RC network. Once that happens, you get the oscillations, and when the AB is just the right value equal to 1 corresponding to the Barkhausen condition, the oscillations will start and you will get the output. Now you also should remember one important point in this, and that is there is a minimum gain that I must ensure in this circuit, the phase shift oscillator, so that oscillations will be produced. So it is not just one condition that the output should be fed back in phase, there should be a positive feedback, that is one of the condition. The second important condition is it should have sufficient gain, the amplifier as such should have sufficient gain. Why is it so? Because you can that to explain that I have shown you a circuit on the screen. You see what you are doing is you are feeding the output voltage at this network, you have got a potential divider with 2, one reactive and resistive component, and take the output across the resistive component, connect to one more RC, then take the R output and again convert one more, and so you have 3 stages of potential division. You divide it once into V1, then again divide it into V2, again divide it into V3. So if this happens, what happens? If this is, for example, if V1 is 50%, if V1 is 50% with reference to V output, then V2 will be again half of that, that means 1/4 of V0. If every one of the network gives 50%, let us assume, then the first network will give half of the input, the second network will be 1/4 of the input V0, and the third will be 1/8 of this. So there will be a continuous reduction, and therefore you have to amplify this to bring it to some level, so that A beta becomes equal to 1. So whatever is a reduction that is happened here, you should amplify. If it is 8 times, you should try to amplify by 8, so that you get A beta equal to 1. That is a whole idea behind this phase shift oscillator, right. So this I call f as the fraction of the output, not frequency. V1 is fraction of V output, V2 is fraction of V input V1, V3 is fraction of V2, and therefore the total is F1, F2, F3 times V0. This F1, F2 if it is the same like 0.5 that I mentioned, it becomes 1/8, right. Therefore the V3 that is actually applied at the input is very small, because it has gone through 3 levels of potential division, and therefore the gain has to be large. You would find when you really analyze the circuit, you would get an expression where you would find the gain of the amplifier for the phase shift oscillator to work should be greater than or equal to 29 to make the A beta equal to 1. Why is it so? We will try to derive the expression also quickly later on, and we also should remember the frequency of this will be given by an expression f is equal to 1 by 2 pi root 6 RC. That root 6 is the factor which is coming in addition to the normal 1 by 2 pi RC for term. So therefore, when you use 3 RC phase shifting network, the output voltage you will find the oscillator works when you maintain a gain which is larger than 29, and the frequency will be given by the expression 1 by 2 pi root 6 RC, where R and C I assume are equal. You can also choose R1 C1, R2 C2, R3 C3, then this expression will become much more complicated, bigger expression. So usually everybody will try to do simple equal values of R and C for all the 3 networks. So when I give equal values for all the 3 networks RC, you would immediately imagine that each of this will produce 60 degrees phase shift. First one produce 60 degrees, the second one produce another 60 degrees, and the third one produce, that is what you all assume. In principle it should be something like that, but in practice it is not. Ideally it is like that, but in actual case it is not like that, because now if I take this R, the potential divider is between the C and this R, that is what you assume. That will be true only if you do not take into account the effect of the presence of these other RC network, because they are all connected in parallel. Therefore the value of R will be affected by these two because they are in parallel combination. Again this R is affected by these RC, etc., and therefore you would not get the same R in each of the stages because of the presence of the other components, and therefore they will never be equal to 60 degrees. You will get almost close to 60 degrees if you observe, but it is not equal to 60 degrees. If you really want to make them equal, then what we have to do is we should isolate each of the RC network from the other. For that I have used a buffered phase shift oscillator, which you can see here. What I have done is the output voltage I connect to RC, but I make sure the presence of other RC are not felt at this point. For that I have used a unity gain buffer, which you know is a very good circuit to produce very high input impedance and very low output impedance with a gain 1, and therefore they only provide high input impedance here. It is so high that the reactive component due to C is the only contribution to the resistance here, and therefore the effect of all the rest of the things that is connected will not be felt here. So this way I isolate segments from the other, and thereby I have used 2 isolators here, the buffers, and when I now give, you would find if I measure the phase shift due to each of the RC network, in this case you would find it will exactly be 60 degrees for a given frequency. So this is what is called the buffered phase shift oscillator. Right, now let us try and see whether we can derive the expression for the phase shift oscillator quickly. I will not give too many details, I will quickly skip some of the intermediate steps. I would expect that you would try to do it on your own and learn. I will give you all the principles involved in that. So I just take one RC network here, C and R, and what is the current? The current is voltage V1 divided by the total resistance by Ohm's law. Therefore V1 I is equal to V1 divided by total resistance is R in series with capacitance, R plus 1 by j omega C. 1 by j omega C is the capacitive reactance. So when I now simplify this, it will become V1 j omega C divided by 1 plus j omega C R. This is what I get. So the voltage across R has a value V2 is equal to current into resistance, again Ohm's law. So I into R. Now if you multiply this I by R, you get V1 j omega C R divided by 1 plus j omega C R. So you can get the value of the output voltage with reference to the input voltage when I apply it across a simple CR network. So now what is going to happen? I am going to connect like this number of three such networks and try to find out, this is V1, V2, V3, etc. Now I am calling this V2 and this I call V4, at this point it is V3, and here I have V1. The phase difference due to one of them is 1 by omega CR, we have already seen that tan phi is equal to 1 by omega CR. Right, now let us try to derive quickly the expression. Now what is V4? V4 is equal to V2 plus I3 divided by j omega c. Why is it like that? V4 is here. What is V4? V4 is the voltage across R plus the voltage across C. The voltage across R is V2, we already know. The voltage across C is I3 into reactance provided by C. Reactance provided by C is 1 by omega c. Therefore you see V4 is equal to V2, the voltage across R, plus I3 into 1 by omega j omega c. Therefore I3 by j omega c. And I3 by, what is I3? I3 is V2 by R. We have seen that I3 is V2 by R. This is I3, this current, and therefore it should be V2 by R. So I3 is V2 by R. So if I substitute this, it becomes V2 plus V2 by j omega c R. I3 I removed by V2 by R, I have replaced. So this is the voltage at V4. Now if I want to look at the next current I2 in the circuit, which is this current, I want this current I2. This current I2 is I3 plus the current through this. So I3 is already known, we have already derived. This current is V4 by R. So that is what I am going to use now. So I3 plus V4 by R is I2. So I now substitute for I3, which we have already got, and I3 is V2 by R plus 1 by R into V2 plus V2 by j omega c R, that is V4. We have calculated this. So when you now combine and then simplify this, it is V2 is common everywhere, V2 into this is 1 by R, this is 1 by R, 2 by R plus 1 by j omega c R square, these two R will become R square. So this is what you get. So now V3 is, I have to multiply this by corresponding number, V4 plus J2 into I mean I2 into the 1 by omega c, j omega c. So you substitute for that again from the earlier expression for V4, and you will get this expression. And similarly you go for one more stage, I1 is I2 plus V3 by R, and you substitute, you get this big expression, and finally you can write V1 in terms of V2. If you go back and look at the circuit, you find V1 and V2, these are the two things that we want. When I apply V1, what is the output? V2. So the final expression you find V1 is equal to V2 into 1 plus 6 by j omega c R minus 5 by omega square c square R square minus 1 by j omega cube c cube R cube. That is what I get. Now what is the condition? The output voltage should be real, and therefore I should make sure the imaginary components in this expression become 0. The imaginary component are basically the second term 6 by j omega c R and 1 by j omega cube c cube R cube. These two terms together should become equal to 0. That is what I have written. 6 by j omega c R minus 1 by j omega cube c cube R cube should be equal to 0. If you simplify this, you get omega square is equal to 1 by 6 c square R square, and omega is 1 by root 6 c R, and omega you know is 2 pi f. Therefore f is equal to 1 by 2 pi root 6 R c R c R. So this is the expression for frequency. So the expression for frequency comes from the condition that the network should have imaginary component 0. If you do that, automatically you get the frequency component. Now what happens at this frequency? What happens? This happens only for one frequency, you should remember that. At this frequency I can now substitute that value in the expression, and you taking only the real part, you will find, because the imaginary part has become 0, so you have 1, you have minus 5 by omega square c square R square. But what is omega square c square R square? You would find from this expression omega square c square R square is nothing but 6. When I take this omega square to the denominator, 6 comes over on this left side to 6, and therefore you find the expression becomes 5 into 6, because 1 by omega c square R square is equal to 6, that is 30, 1 minus 30 is minus 29, 29 V2. So the output becomes V1 is equal to minus 29 times V2, or V2 is 1 by 29 times of V1 with a 180 degree phase difference minus, that minus shows it is phase difference also. So when will this become equal to 1? Only when the gain becomes 21, this is the beta factor 1 by 29. When the gain becomes 29, A beta becomes 29 into 1 by 29 is equal to 1. Therefore, it will satisfy the Barkhasen's condition. You will get 180 degree phase also, and therefore the oscillations will be sustained. So this is what we have in the RC phase shift network. When A is equal to 29, this product becomes 1, that is satisfied as the Barkhasen condition. So with this background, we have now discussed how you can make a phase shift oscillator using an operational amplifier using 3 RC network, and it is very convenient because RC are all very cheap component. You do not have to have very expensive things, and then you can easily vary them, change them, and modify the frequency of the output waveform, and therefore it is very convenient to design, simple to design, and therefore I will show you a demonstration of the phase shift oscillator using operational amplifier. So you can see here the circuit. It is the same circuit which I showed you just now on the screen. You have the operational amplifier in the inverting mode with R1, R2, this is 2K, this is 100K, so there is a gain of about 50. You can even make this as variable. I think I have used it as a variable potentiometer here, and therefore when I vary this, I can get a gain which is larger than 29 very easily by modifying the R2 by R1 ratio. So this is a inverting amplifier because you are connecting to the minus input. It is an inverting amplifier, therefore there is a 180 degree phase shift here. That output I take and give it to series of 3 RC. They are all 0.1 microfarad 1K equal values. You can see in the circuit here 3 1K resistors and 3 0.1 microfarads here, and that output is connected to the input pin number 2 of the operational amplifier that you see here. And for the feedback resistor, I have used a potentiometer carbon resistor here, and the output is monitored using the oscillator or using the oscilloscope. To determine the frequency of oscillation, I am also connecting a function generator here. You can see that this is a function generator. So you can select different frequency scales here, 1, 10, 100, etc., and you can vary the frequency using these 2 knobs. One is for fast variation, the other one is for slow variation, coarse and fine, and you have here output voltages which again for coarse and fine you can vary the amplitude, and the output of this I connected to another channel of the oscilloscope. In the oscilloscope you see 2 channels. I will show you. So now if I change the frequency in the oscilloscope, you can see the 2 signals are seen. This steady one is due to the oscillator that we have constructed. This one is from the oscillator, standard oscillator that I have used. So now what I am trying to do is I am trying to superpose them and measure the frequency. So I am using the oscilloscope to bring them together, and if necessary increase the amplitude, make the amplitude equal. I have made them almost equal amplitude, and then I will slowly change the frequency till you get some coincidence. This is almost coinciding except for the, you can see that. Let me try to adjust it steadily. So you see when it is coinciding, there is a continuous phase factor which is coming, that is why it keeps on moving. So if you arrest them both, you would find the frequency is almost the same. So it is around 636, that is what you see here. This is the frequency, and if you actually calculate 1 by 2 pi RC with R 1 kilo ohm and C 0.1, you will get close to 600 ohms, 600 hertz. But you may not get exact value, and that is because there is also a tolerance of these resistors and the capacitors. You all know that. Because of that you will not get an exact value, but you should get very close value corresponding to 600 hertz. Now how do you know this is the output waveform that I get is due to the oscillator. Now I am varying the gain factor here. You can see that when I get very high amplitude. See, this is the, when I change that, now I do not get any oscillation. Now when I change it, when the right gain about 29 or so I get, you see on the oscilloscope the building up of the sine wave. Now the sine wave builds up, it goes up to that, and if I now reduce, it goes to 0. Therefore it is only the output from the wave from the circuit that I get on the oscilloscope, and that is what I now when I change it to XY mode, you would find when you get a straight line. Let me get the waveform back and then adjust the frequency in the XY mode. I am now making it X and Y and try to adjust till I get a circle. I should try with this. Yeah, you get a circle here. When will you get this? Is Lissajous pattern. When the two frequencies, the frequency of the oscillator that we have constructed using the operation amplifier and the frequency from the function generator, when both of them match, I will get a circle on the screen. That is what that shows the two frequencies are equal. Now if I make it into the dual slope, you find both the sine waves are almost coinciding and the frequency is the same. So this corresponds to there are two ways in which you can measure the frequency. One is by comparing with another oscillator, the other one is using the XY mode and trying to generate the Lissajous pattern. That is what we have just now done. So you have a phase shift oscillator here using op amp, and the output has been measured and the frequency also has been measured. Now we will go on to our next circuit, which is again an oscillator, and again it uses RC network, and that is called the Wien's bridge oscillator. What is a Wien's bridge? You can see on the screen a combination of RC again, but one RC is in series, the other RC is in parallel. So when I have RC in series and RC in parallel, this combination is what is called the Wien's network. Wien is the one who found that when I give an input here, the output comes from this will be at 0 phase. That is for a given frequency. That is a property of this Wien's network, and phase is 0 and the frequency is 1 by 2 pi RC. And when you really do the investigation, just as you did for the case of the phase shift oscillator, you find the gain will have to be at least 3, either equal to or greater than 3. So these are the important points with reference to Wien's bridge, and one can also obtain the expression. I have given the just expression which you can perhaps test later on by using 1 R by RCS plus 1. This expression will actually can be worked out on your own, and you would find this will also lead to the corresponding gain should be greater than 3 and the phase shift will become 0. Now this RC Wien's bridge network can be used for generating frequencies in the range nearly 5 Hz to 1 megahertz. This is the greatest advantage of the Wien's bridge oscillator built on the Wien's network. You see, when you want a variable frequency oscillator, everybody wants a variable frequency oscillator. You just now saw a function generator which I used where I was turning a knob and the frequency was changing. If you want to do that in the RC phase shift network, you find you have got 3 resistors and 3 capacitors. You have to adjust them, all of them either equally or differently. So it becomes very cumbersome to have too many components to vary. Now in the case of Wien's bridge, you have only 2R and 2C. Usually C is switched for decades and the resistance is varied for changing the frequency in between. So it is very convenient, more convenient than RC phase shift network, to use the Wien's bridge in the oscillator circuit. So I have also shown a small analysis. If you do that, you would find the beta factor will be 1 by root 9 minus xc by r minus r by xc whole square. The phase factor tan phi is equal to xc by r minus r by xc whole divided by 3. These two expressions can be derived by using a simple network IDM. I leave it to you to as an exercise. And what is important is when xc becomes r, you would find that corresponds to the condition r is equal to 1 by 2 pi frc, where fr is the critical frequency. You would find you get a maximum at that point, the fraction, and that is corresponding to 1 by 3. Beta will become 1 by 3. So the frequency is therefore 1, if from this expression I am getting frequency is 1 by 2 pi RC, and the phase actually goes at that frequency, the x axis is frequency, at that frequency the phase goes to 0, before it is minus plus 90 and beyond it is minus 90, and so in between it crosses the 0, and when it crosses a 0 the corresponding factor is 1 by 3, the feedback ratio, and that gives me an expression for the frequency as 1 by 2 pi RC. I have now shown you the full circuit using op amp. This also can be constructed using transistors. So when I have the Wien's bridge oscillator, I have an op amp, and you can see the Wien's bridge component coming here, RC in series and RC in parallel, and the output at 1 with reference to 3 is the output voltage of the op amp, 1 is the feedback voltage that is given. Because it is in phase, the feedback is given to the plus, already it is 0, therefore there is no need to provide any additional feedback as in the case of the phase shift network. Therefore the output 1 is directly connected to the plus terminal in the picture, and therefore it becomes positive feedback. Now in the negative side I have used some 2R and R, 2R prime and R prime, and because now what happens to this configuration, I do not know whether you are able to recognize the configuration. I am giving the signal to the non-inverting input, and the inverting input is grounded through a resistor R prime, and 2R is the feedback ratio, feedback resistance. So the gain of this will be 1 plus R2 by R1, we all know that for non-inverting amplifier. R2 is 2R, so 2R prime by R prime is 2, 1 plus 2 is 3, therefore the gain will be 3. That is what Wien's bridge condition says, the gain should be greater than 3. So now you also normally have here the resistance which is connected to the inverting input. You do not use normal resistor, you use a tungsten lamp, a small lamp you can put. Why do you put the tungsten lamp? Because the tungsten lamp, when the resistance is there, it is not for glowing, the bulb will not glow at all. For the low current that we are going to send, the bulb will not glow, but then when the current flows through that, it will produce a heat. So when the heat is produced, the resistance becomes larger due to thermal effect, and when resistance becomes larger, it will control the gain, right. The 2R by R factor will become smaller, and therefore it will provide a negative feedback to introduce a stability in the amplifier oscillator, and therefore it is normal to use a tungsten lamp in here. We will now use without the tungsten lamp, but one can also use the tungsten lamp, and the expression becomes very simple. I have shown the same circuit, this is the same circuit, but I have shown it in the form of bridge, because we all know the Wheaton's bridge. This is Wien's bridge. You have R1, R2, R and C in series, R and C in parallel, forming the 4 arms of a Wheaton's bridge, and the first 2 arms are given to the output and the ground, and the other one is given to the 2 inputs. So this is a Wien's bridge oscillator, and it uses positive feedback and also negative feedback for stability, and it is a very simple circuit to get the oscillations at the output. And here again AB should be equal to 1, as we have already seen, and that is what I have shown here. The closed loop gain is 2R prime by R prime plus 1, which is equal to 3 in this case, and the beta is 1 by 3 we have already seen, therefore 3 into 1 by 3 is 1, that corresponds to Bar-Cousins condition. Right, now let me show you an actual working circuit of the Wien's bridge oscillator. We have seen now 2 different types of oscillator circuits. One is RC phase shift oscillator, the other one is the Wien's bridge oscillator, both are RC oscillator. Now I want to quickly show you a third type of RC oscillator, which is called twin T oscillator. It is called twin T because you will find there will be 2 T networks. You have, I hope you can see on the screen, you have got 2 capacitors connected in series and 1 resistor here in the form of a T network. You also see 2 resistors connected in series and a capacitor is at the stem. So this is one T, this is another T, both of them are combined together to form a network, Therefore, this network is called twin T, 1 T here, 1 T here, 2 T's what we call twin T. So, the twin T network also, like the Vn's network, provides 0 phase shift. So, V in is there, V output is there, they are in phase for a given frequency. So, it is a very simple scheme, and I have shown here how the phase is varying. For example, from 0 it goes to maximum minus 90 and comes to 0 again and goes to plus 90 and 0. So, this point where it crosses, you find the it gives 0 output. It is actually a notch network. It will pass everything else except that frequency, it will not pass at that stage. That is what it gives 0 output at this point. V output, V in gain is 0 for that particular frequency. Phase also is 0, output is also 0. So, and that condition is the frequency is 1 by 2 pi RC. So, it is very similar to Vn's bridge, very simple to construct, and therefore, this is also a very useful circuit. So, we have formed a simple Vn's bridge network here, and you can see the circuit is very similar to what we have done in the case of Vn's bridge. We take the output and give through the twin T network and connect it to the input. So, this is used in the feedback network, so with 0 phase shift. So, once you do that, you get an oscillator output which is again in the form of sine wave, and you can the values of the capacitor and C is given here. If the value of capacitor is C in the T network, then in the other network it has to be 2C, and the resistor R, and in the other network it will be R by 2, and so you have the twin T network connected in the feedback point of the operational amplifier, and you get an output which is corresponding to a twin T oscillator. I will show you just the demo. Here I have the circuit of the twin T network. You can see the 1 T here, 1 T here. The corresponding circuit is shown with the 2 resistors and 1 capacitor, and the 2 resistors and 1 capacitor here. So, this is a twin T network, and you have the operational amplifier, and one of the resistor here is made as a variable resistor for adjusting the gain, and you observe in the oscilloscope that sine wave generated due to the twin T network. If I vary the potentiometer, you would find I will be able to get the oscillations. Now, I have got the 2 channels of the oscilloscope. I have connected. This is the output from the oscillator, this is the output from the standard oscillator, this is from the circuit, and therefore, I want to compare the frequencies. Now, I will adjust the frequency to larger values and try to get the. So, I keep adjusting the frequency so that they both match. Now, if I coincide them and make them go slowly, you would find the 2 frequencies will almost match. Is it matching? The better way is to use the circle. So, when I get a circle Lissajous pattern, the frequencies should be matched perfectly. The frequency is about 1.84 kilohertz for the component that I have used. Now, you can see the 2 frequencies match very well even when I put it that way. So, the values of resistors are 10K and 0.1 microfarad. This is 10K, the 2 resistors, and the capacitors are 0.1 microfarad, and therefore, this will be 2C, that means 2 times 0.1, 0.2 microfarad. They have put actually parallel capacitors are put there to make add, and this is 5K, they have put again resistors in parallel to make this 5K, or you can use 4.7K. So, you find a very simple sinusoidal oscillator can be constructed using twin T network. So, thus we have seen in this lecture 3 different types of oscillator circuits built using op amp. One is the RC phase shift oscillator, the other one is the Wien's bridge oscillator, and the third one twin T network oscillator. All the three are very useful, but the most useful among them will be the Wien's bridge, because it is much easier to vary the R and C components. You can have ganged resistors and ganged capacitors, and you can vary the thing. Most of the oscillators that you get commercially in the low frequencies less than 1 megahertz are based on mostly Wien's bridge oscillator. Thank you.